Okay, well, the recording has started. Welcome to the Air Fluxes from Space webinar series. Today we have Marco Larrañaga, um, who's going to talk about partial control of the Gulf of Mexico dynamics by the current feedback. And Marco is just started a postdoc at Florida State University. He previously did his PhD and an initial postdoc in Toulouse, France. So I'll let you take it away, Marco.
Thank you. Well, hi everyone. Thanks so much for attending this presentation. And well, in this presentation, I'm going to talk about how sensible is the Gulf of Mexico ocean dynamics to the current feedback to the atmosphere. Well, I know that everybody is used to talk here about the current feedback, but this is going to reduce the kinetic energy at the mesoscale, as I show you in this example from 2016. Here we have an estimation of the eddy kinetic energy from altimeters, from an uncoupled simulation and a coupled simulation that include the current feedback to the atmosphere. And as we can see, the coupled simulation is more realistic, it's more similar to the Abiso estimations, but the uncoupled simulation have an excess of eddy kinetic energy. So by properly reproducing the eddy kinetic energy at the mesoscale, we are also going to better reproduce the mean currents. So for example, here we have the mean Gulf Stream path over 5 years. In red, we have the Abiso estimations. In black, we have the coupled simulation estimations. And in blue, we have the uncoupled estimations. So the coupled and Abiso are super similar. The coupled simulation is realistic, but the uncoupled occupates a larger area. And that's because when we have a larger eddies with a larger eddy kinetic energy, we are going to have more eddy mean flow interactions. They are going to produce meanders in the mean kinetic energy. So just to include the current feedback in numerical simulation, what we have to do is compute the wind stress as a function of the winds relative to the currents. But in fact, how is that the wind work? Well, it's going to modulate the energy transfer between the atmosphere and the ocean through the wind work. That is the average of the wind stress and the currents, surface currents. So if we separate the wind stress into the mean part and the anomalies to a Reynolds decomposition, for example, that's where we are going to understand how it works, because here is where we have the mesoscale. So we're going to explain that with this cartoon. So if we suppose that we have an homogeneous wind, that is are the black arrows, that is blowing over an eddy, no matter if it's a clockwise or anti-clockwise eddy. At the regions where the winds that we have in black are blowing at the same direction that the currents, just by the definition of the wind stress, we're going to reduce the wind stress. And by reducing the wind stress, as the wind stress and the currents have the same direction, we are going to have positive eddy wind work, geostrophic eddy wind work, which means that the atmosphere is going to force the ocean, is going to give energy to the ocean. But as the wind stress is smaller, we're going to have a smaller energy flux. But here, where the winds blow at the opposite direction that the currents, we are going to increase the wind stress. And as they have different direction, we are going to have a negative eddy wind work, which means that the ocean is going to sink energy to the atmosphere. As we have a stronger wind stress, we're going to sink more energy from the eddy to the atmosphere. So if we spatially integrate this, flux, the sink of energy from the ocean to the atmosphere is going to dominate, and that's how we awake the mesoscale. So if we put attention here, we are going to see that, for example, here we have a clockwise eddy, and that eddy is going to induce a counterclockwise wind stress curve anomalies, right? So if we relate the current vorticity with the wind stress anomalies vorticity, we are going to see that there is a negative relationship, but also the steep of the relationship is going to give us the coupling coefficients that reflect the strength of the current feedback. So if we make maps of that, we're going to see that the current feedback is important everywhere, but it's most important at the region that we have a lot of mesoscale, like in the Gulf Stream, in the Kuroshio currents, in the Agulas, but it's important everywhere. So that gives us a question like, for example, which are the consequences of reducing the eddy kinetic energy in regional ocean dynamics? So to try to answer that questions, we do numerical simulations over the Gulf Stream. That is a region rich of mesoscale eddies, as I'm going to show you. So the Gulf of Mexico located at the west of the Atlantic Ocean, and its dynamic is dominated by the emblematic loop current, that is this current. Um, this current starts at the Yucatan Channel and ends at the Florida Strait. And this current constantly is detaching these large anticyclonic eddies that are called loop current eddies. And those eddies can be reattached several times until they find a separation that is going to occur when the eddies are able to travel to the west. So these eddies are important to the Gulf of Mexico dynamics because they are an important source of heat. They transport heat water from the Caribbean into the Gulf of Mexico, and they are spreading this heat water until they uh, travels to the west. But also, we know that this region have a lot of hurricanes, and in fact, those eddies can intensify the hurricanes through the heat fluxes. We can also see in this animation a small cyclonic eddies traveling all around the loop current, and those eddies seems to modify the loop current shape, but also seems that they are related to the detachment and separation of loop current eddies. But also, as I'm showing this new animation, they can, it's about the kinetic energy. They can produce pulses of kinetic energy when they interact with the loop current through barotropic and baroclinic instabilities. So as we see, the Gulf of Mexico is rich of mesoscale eddies, and that's why it's important. It's a good region to see to study the current feedback. So about numerical simulations, I mean, forced or coupled numerical simulations without the current feedback can reproduce the main dynamic characteristics of Mexico. For example, the loop current is able to grow, to detach, and to separate loop current eddies. But when we compare, for example, the kinetic energy or the eddy kinetic energy of altimetric observations with numerical simulations without the current feedback, we are going to see that they overestimate the eddy kinetic energy. But also, they have problems in reproducing the mean loop current extension. They underestimated in comparison with altimetric observations. But they also underestimate the number of detachments, but also they largely underestimate the number of separations. But as we know, the current feedback help us to reduce the excess of eddy kinetic energy at the mesoscale, and also help us to better reproduce large scale currents or permanent currents like the loop current. So the objective of this work is try to assess the extent to which the current feedback can modulate the Gulf of Mexico ocean dynamics. And to do that, we use coupled numerical simulations. We use NEMO to reproduce the ocean dynamics with a resolution of 8 kilometers. With that, we are able to reproduce a lot of scales of the mesoscale. And we use the WRF model to reproduce the atmosphere dynamics with a resolution of 25 kilometers. And we coupled these models with OASIS, which allowed us to exchange early average of data between the models. And the length of the simulation was 24 years over this domain, right? So we do two experiments. We perform two experiments. No current feedback, in which we compute the wind stress as a function of the absolute wind, and also the current feedback experiment, in which we compute the wind stress as a function of the winds relative to the currents. So by comparing these two experiments, we are going to see the sensitivities of the Gulf of Mexico ocean dynamics to the current feedback, but we are also going to compare with altimetric observations when we can to see if the change that we have are realistic or not. So first, we are going to start with an eddy kinetic energy budget of the most important terms. Here I show you the geostrophic eddy windward for the no current feedback simulation and the current feedback simulation. And here I have the spatially integrated terms. I integrated terms over the loop current region that is delimited by this segmented line polygon. And I also use the data outside of the platform that is delimited by this 200-meter deep contour, right? So in the no current feedback experiment, we have like positive and alternating values of geostrophic eddy windward. And if we spatially integrate them, we're going to see that we have a predominant positive fluxes, which means that the atmosphere is in fact forcing the atmosphere, is injecting energy to the mesoscale eddies, sorry. And in the current feedback experiment, we have negative fluxes, which means that the ocean is sinking energy to the atmosphere. And if we spatially integrate them, we are going to see that they are at least the double or twice the stronger than the ones that we have in the no current feedback, but they are negative. So these have like indirect effects on the eddy kinetic energy budget. For example, we are going to reduce the production of eddy kinetic energy through barotropic instabilities that are related to the horizontal shear of the currents. And seems that by reducing the energy or the production of energy in the region, we are going to the ocean is going to try to stratify. So we are going to have a larger baroclinic instabilities. But barotropic the difference in barotropic and baroclinic instabilities, I mean, they got canceled. So the difference in the production of eddy kinetic energy is mainly related to the eddy windward, geostrophic eddy windward. So by changing that, we change the eddy kinetic energy as we see here. From no current feedback to current feedback, we have like 20% less eddy kinetic energy, and the current feedback estimations are more similar to the observations. But by doing that, we are going to have a lot of indirect effects. For example, we are going to increase the penetration of the loop current into the Gulf of Mexico because of the current feedback. We are going to improve the number of detachments, of eddy detachments, but also we are going to largely improve the number of eddies that completely separate from the loop current. But not just that, we also are going to change the eddy trajectories. For example, here I show you the position of the eddies after being detached over the 24 years with the squares, and then with the lines I show you the eddy's trajectory, and with the circle I show you the last position of the eddy where the eddies die. And I show you this for the Aviso, the no current feedback experiment, and the current feedback experiment. And as we can see, the position of the detached eddies, the initial position is well reproduced by the current feedback in comparison with Aviso. They are similar, as well as the eddy trajectories. So to do that, to do that or see that better, we use an histogram of the eddies that cross this transect. As we can see, Aviso, that is the gray, and the current feedback, that is the blue, seems that to travel to two well-defined highways that are centered in 24 degrees of latitude and 26 degrees of latitude. And the eddies seems to die at the same regions in the current feedback experiment and in the observations. But in the no current feedback experiment, the detachment seems to occur south, and the trajectory seems to be shifted south, as well as the region where the eddies die. And by in colors, I show you the eddy kinetic energy, and as we can see, we overestimate the eddy kinetic energy in this region in the no current feedback experiment. It seems to be related to the occurrence of loop current eddies. So to dig on that, what we do was to compute the average of the kinetic energy of the separated eddies, as well as their lifetime. As we can see in the no current feedback experiment, we have a more energetic eddies. So if they are more energetics, they are going to need more time to dissipate their energy, so the lifetime is longer. So seems that they are the responsibles to have these larger eddy kinetic energy values here. But if this could have like important consequences in the Gulf of Mexico dynamics, since those eddies are the ones that carry the hot water into the from the Caribbean into the Gulf of Mexico, and that's supposed that they have to spread the water as long as they travel to the west. But if they take a lot of time to die, they are going to spread more water here than here. So that takes us to the question that if the properties of the eddies in terms of salinity and temperature change with the current feedback. So we do composite of all the separated eddies from the current feedback experiment and the no current feedback experiment for temperature and salinity, and we compared with glider observations from a really large eddy called Poseidon. So here we have the temperature and salinity. We can see that in the temperature we have like a well-defined eddy core that have like a shape of a pancake or a pot. And in the salinity, we have two cores, one at the surface with that can reach that 200-meter depth, that is fresher, and another one below the 200-meter depth that seems to be salty. So in the composites of our simulations, the current feedback seems to properly reproduce the warm core, and seems to reproduce the two eddy cores at the salinity, the fresher one and the salty one. But in the no current feedback experiment, uh, for example, here looking at the 25 thermaline, we see that at the middle of the eddy, it's go deeper than in the current feedback experiment, and which means that those eddies are in the no current feedback experiment are going to have a larger eddy content. So, for example, if we use these results to trying to forecast the occurrence of or the intensification of hurricanes, we are going to overestimate their heat fluxes, and we are going to over intensify hurricanes. And for example, in the salinity, we also see that we have a larger salinity or yeah, stronger salinity at the surface, and we miss the two eddy cores. I mean, there's only one core that is well mixed. So the current feedback largely modify the properties of the eddies that are detached from the loop current. And well, if we go back to this figure, as you remember, we said like seems that in the no current feedback experiment, the eddy seems to be detached south. So to dig in that, what we do was compute the position of the loop current where is cut it to when detach an eddy, and we do maps of that. Here we have an aviso, no current feedback, and current feedback maps. And as we can see, the no current feedback have detachments south. They're, most of them are shifted south, but when we have the current feedback, we improve the occurrence of detachment north, but we are missing some of the variability that we have in Aviso. We are still having a bit problems, but we are doing better with the current feedback. So if we classify these detachments along the latitude with these histograms, but also we separate into retached and separated, we are going to have a lot of information. For example, for Aviso that is a gray, it seems that is more prone to produce retachments in southern latitude, and seems to is more prone to produce separations in northern latitudes. And well, the current feedback experiment is properly resolving that, but they have a bit of problems in the southern separation retachments. They have like a bit larger retachments in comparison with Aviso, but it's doing better than no current feedback. And about the separations, is doing well, but have some problems in the northern separations that we saw in the figures above. But the no current feedback, as we saw, lack of separations, but have a lot of problems in the south retachments. They have unrealistic values. So if we are cutting and cutting the loop current in the southern region, we are going to decrease the mean loop current penetration. So that's why we have the reduced mean loop current penetration. So just as a summary, I think we largely demonstrate that the current feedbacks largely modulate the Gulf of Mexico ocean dynamics. First, by reducing the eddy kinetic energy in about 20% through the geostrophic eddy wind work, and that have many indirect effects. For example, we reduce the excessive occurrence of reattachments south of the loop current, and with that, we are going to improve the realistic loop current eddy detachments, and we are going to promote a more realistic loop current extension, and we are going to have more realistic loop current eddy trajectories and properties. So if you are interested in this work, we published in Journal of Physical Oceanography in 2022, and I invite you to read it. And that's it for the presentation. Thank you so much.
Thank you very much. Questions for Marco? And maybe while people are thinking of questions, I'll ask about you mentioned that the difference between having the current feedback and not having it would impact heat transport and heat loss to or fueling of hurricanes. Have you made an effort to quantify what that impact would be? Do you know how much it might affect a hurricane?
No, we haven't done that right now. We have plans.
Mhm.
Here we have two important atmosphere features. For example, ones are the hurricanes, but also we have strong cold fronts that are recurrent. At the winter, we have like 20 per year.
Mhm.
And those winds are dry and at least more than 10 meters per second velocity. And as we have a lot of eddies, we are trying to composite of that to try to see what happened with the energy fluxes in terms of the wind work, but also the heat fluxes and humid fluxes also.
Mhm.
And we have planned one simulation for try to see. There's one case where we have a really big eddy here, and one hurricane cross over the eddy and kill the eddy. So we're trying to see if we can simulate that
Mhm.
to try to quantify that.
Other questions? I'm also curious. I know that the southern part of the Gulf of Mexico has some of the strongest diurnal winds in the world. Have you thought about what an impact a diurnal wind variability, a sea breeze type circulation might have on the current feedback? Has anybody tried to couple those together or combine them?
Yeah, I haven't seen that, but it's a bit tricky because the frequency is like about like a daily frequency of the breezes, so it's like
Mhm.
mixed with the air rotation frequency.
Mhm.
And I use I mean I this is those simulations are a bit costly, so I use daily average to
Mhm.
analyze it, so I lose I lose that data. But yeah, perhaps it will be nice to study that. I'm not
Yeah, I
sure
think
how deep go the breezes into the Gulf of Mexico, but
yeah, I think they were discovered in the Gulf of Campeche by the pirate Dampier. So um, so they're really obvious there, or they were in
yeah.
1700s when he got stuck. Yeah, so I guess you have an interaction between the diurnal winds potentially and the near inertial or inertial oscillations and all the other dynamics. And as you say, everybody tries to suppress that. So, any other questions? If not, thank you for a really nice and succinct discussion.
No, thank you to you.
Really
Thanks everybody.
appreciate you. So, thanks everyone. We will take a summer hiatus after this. I know people have a lot of travel and vacations, and we'll pick back up probably in September. So, Thanks, everyone.
So, thank you.
Thank you.